Hello, everybody. If you would mute yourself, I think somebody's stereo is in the background. We'll go ahead and get started with our February 1st, welcome to February, gathering for a lecture today. Today's lecture is going to be a lot about alkenes. Do you remember that second functional group that we had discussed in terms of the hydrocarbons? So initially we talked about alkenes being anything that has one or more. We're going to talk about a particular compound today that has a whole lot more than one double bond, multiple double bonds. And that'll be towards the end of today's lecture regarding basically vision. We'll talk about the chemistry of vision when we get to that point. Before we get too far along, some good news. So I got on to the website this morning, the NC State COVID website, and it looks like, let me see if I can find it for you here. NCSU. Just give me a second, I'll share my screen with you. Take a second to come up. Takes a minute. This is a site, and probably you've all gone on this before. You know, the NCSU board here. So let me get to NCSU real quick. You can, and if you haven't looked at this is always a good site to get on, just to give yourself a lot of information regarding how things are going. Give me just a minute, a second. Now I don't think they've updated the stats for today, but hopefully soon. If not today, they'll definitely update it by tonight. So let me open up the dashboard here. Okay, all right, now let me get back to our Zoom and I'll share my screen with you. Share screen. Okay, so can everybody kind of look at the graphic here? So this is showing positivity in cases and whatnot. So, you know, you can look at the early January data. Here's where we were at the start of class, way up here. You know, 400 cases, 450, 475. Then we had a little bump and then it came down. And now we're here. Here's January 25th last week. And you see, look at this trend. Bunk, 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 bunk. Now this will be updated. So we are definitely heading well in the right direction. So this is looking really, really good. I hate to say it too much because, you know, one never knows, things can change. However, the COVID cases have rapidly declined, and so I'm assuming that will continue as long as there's no new variant, which the CDC has not mentioned anything about any new variants. So that's good. So next week, I'm going to go ahead and pull the trigger and say next week we'll be in class. And like I said before, if you, this will be on a Pompano lecture as well. So if you can't make it, don't worry about it. It will be recorded. You can look at it at your leisure. But that does bode very well for not next week, but the week after that is our exams, our first exam. So that looks great. Currently, we have about 218 people total in the class. Several a lot of people have dropped since the beginning. We started out with 241 and now we're down to 218. I guess I scared a bunch of people off. But the other part of that is we have quite a few people who will be taking their exam at DSO. So that will open up a lot of seats in the class for the exam. And then the university has added in that particular classroom 20 new seats at the way back along the benches. So that increases the capacity for the classroom. So for a lot of reasons, it looks really promising. I don't think there'll be too many issues related to our exam in a couple of weeks. So that looks great. For those of you who really need the extra space, we've arranged for several seats to be at minimum 20 feet, which is 3 times what they recommended in a normal distancing away from anybody else. All right, so let's get away from COVID now and let's get to our class. All right, so let me go ahead and bring up, we've got a lot to do today. So let me go ahead and bring up my lecture notes real quick. Share my screen. Oh, nope, that's still that. Don't want that. Let me go back and I will share my screen. And where's my, here it is. Enter. And I need to make this a little bit bigger.
Dr. Brown, you have people in the chat that have questions.
Okay. Go ahead and unmute yourself and let me answer the question, and then we can all make sure it's chemistry questions, not personal questions. If it's personal questions, send me an email. Don't do it through chat. But if it's a sort of a general question related to the class or to chemistry, go ahead and unmute yourself and ask me your question. Anybody? Hello? Can anybody hear me? So if you got a question in the chat, go ahead and verbally let me know what your question is.
The person that asked the question says they can't unmute themselves, but she asked if we get COVID, are we still able to get Kahoot points?
If you get COVID, can you get Kahoot points?
I think she's asking, can we watch it like live and do the Kahoot?
You're right, exactly. So just like you're doing right now, we're not together. It's going to be the same thing when we're in person. It'll be streamed. So those people who can't make it to class can look at it and do any Kahoots. You could just get on your Kahoot and you could do your Kahoots just virtually. And those people who are in class, they can just do the Kahoots, while they are there.
Is there any way?
What's the problem with not, who can't mute themselves? That should not be an issue. Everybody should be able to unmute yourself.
Is there
I think she's just in a quiet place. Like it's not because of her computer, it's because of her location.
Oh, I did not know that's a thing. A quiet place. Okay, I'll have to educate myself on what is a quiet place. I didn't know that was something in Zoom, that there are these areas of the country that are quiet. Okay, I will educate.
She's like sitting
Probably
in public.
like a library.
A library? Oh, I see. So if you're at the library, you mute yourself so you don't disturb other people?
Yes.
Ah, okay. I see.
I have another question.
Sure. Go ahead.
Is there any way that you can like add time for the Kahoots? Because like it lags on Zoom and like when you're on live and like.
Oh yeah, sure. I can double that time. So instead of 30 seconds, I'll make it 60 seconds.
Okay, thank you.
Yeah, no problem. I didn't realize that was an issue. Yeah, for sure.
Excuse me, Dr. Brown.
Yeah, go ahead.
I've got a question about the test that's going to happen on February 17th, I believe. I was wondering,
Sure.
if you were going to post like a study guide or an outline of what we've done so far, because with the transition to in-person classes, I don't want to lose track of any information.
That's already ongoing. So get on to the Moodle page and you will see a section of the Moodle page that says, what should I know? I think it's like the third or fourth block of things on your Moodle page. That is your material that you need to know for the exam. So go to what should I know, and week by week, every week I do this week, this is the stuff we learned, and this is the stuff I should know. Now,
Okay,
in addition to
perfect.
that, the day before the test, I'm sorry, not the day before, the lecture before the exam, we also have a review. So we'll go over that same list that's in the Moodle. We'll go over that together in the lecture. So, but yeah, you already have everything we've done since the start of class.
Okay, perfect. Thank you so much. I just didn't want to miss anything.
No, you got it all. It's just go onto the Moodle page and look at all those topics. Anybody else? No? Okay. All right. Let me go ahead and get back to our meeting here real quick. And pull this over just a slight bit so I can see everything on my screen. I guess you could see it. All right, so let us start our lecture for today. Now, in previous lectures, we learned how to convert, and I'm circling it right now. This is ethane. How we can convert a hydrocarbon, a saturated hydrocarbon, with molecular bromine and light. This is that free radical halogenation. So basically, we're substituting that hydrogen right here for a bromine atom. Here it is in the product. The byproduct is HBr. That's a gas. So the nice thing about this reaction, you know it's working because the HBr gas just starts to bubble out. By the way, you would never want to do this in the open air because HBr gas, if you breathe it in, becomes hydrobromic acid in your lungs. And that would be devastating. You would die. So you would have to either trap this acidic gas, or you would have to put it in the hood, which would carefully take away this dangerous gas. But here's the product: bromoethane. Bromoethane. Now, this is a reaction. This is a reaction of alkyl halides. So every time that we do chemistry, or a lot of these functional group chemistries, let me tell you. So the first part that we learn is, how do we make them? Where do they come from? Now, in the case of the hydrocarbons back here, that was predominantly from that, at least what we know so far. These molecules, they came from the distillation of petroleum. So that really wasn't a synthesis reaction, although we can synthesize this, but we got most of that from petroleum. Now, this is from a free radical halogenation. That's what the light does. The light breaks apart the bromine into two bromine radicals, and then that substitutes for the Br. That was the fodder for our last lecture. All right, so here is our starting material for alkenes. This is one way to make alkenes, by the way. There are other ways, and I'll show you that as well. The one particular way we're going to do actually today towards the end of lecture, where we can make alkenes not from alkyl halides, but from alcohols. We'll create alkenes from alcohols. But let's not get ahead of ourselves. Let's go ahead and create alkenes from alkyl halides. This is known as elimination or beta elimination. This particular elimination is called an E2. What does E2 stand for? E2 is the number of starting materials that are required to get to the transition state of this reaction. That's what the 2 stands for. E stands for elimination, The 2 stands for bimolecular. Bi means 2, like bicycle. You have 2 wheels on a bicycle, right? So we have the base and we have our substrate. This ethyl bromide is called the substrate. The base is some base. You know what bases are, like sodium hydroxide is a base, sodium hydride is a base. There's a lot of different bases out there. What does a base do? The base takes a proton, an H, off of a molecule. That's what Bronsted acid bases do. A Bronsted acid donates a proton. A Bronsted base takes the proton. So this is initially a Bronsted acid-base reaction, but we could look at that as a Lewis acid-base reaction too. Remember, that's opposite. A Lewis acid is an electron acceptor. A Lewis base is an electron donor. All right, but in this case, here we have some negative thing. Let's say it's hydroxide, OH minus. So this pair of electrons pulls the hydrogen. Now here's the thing, adjacent, the hydrogen on the carbon next to the carbon that holds the leaving group, the bromine. So let's get used to some terminology here. The carbon that holds the bromine, the halogen, that's called the alpha carbon. The carbon that's next to the alpha carbon is called the beta carbon. That's why it's this reaction is sometimes called beta elimination, because we're pulling the hydrogen off the beta carbon. All right, so this bonding pair, this sigma bond, comes down after the base pulls this hydrogen off and knocks the bromine off to create a new bond. Okay, this is called an alkene, this molecule, a carbon-carbon double bond, one or more carbon-carbon double bonds, belongs to the hydrocarbon class alkenes. So this is called ethylene, by the way, ethylene. Or, you know, we're going to later on, not this lecture, next lecture, we're going to polymerize this to make polyethylene. You're probably holding something right now that is made of polyethylene polymer. Now let's talk about this double bond here for a second. So we have this sigma bond, and it didn't go anywhere. The sigma bond is the bond between two nuclei, between two atoms. So it's still there. There's the sigma bond. Here it is. Here it is. So it hasn't gone anywhere. But we have a new bond, don't we? This second bond between the two carbon-carbon atoms, that is known as a pi bond. So we have sigma bonds. So anytime two atoms are bonded, that first bond is always the sigma bond. Okay, that is a must. So if two atoms are connected, there has to be one sigma bond. Now here's the other thing. There can only be one sigma bond. So anything more than one bond, those bonds have to be pi bonds. Now, here we have one pi bond and one sigma bond. Now, do you remember the molecule acetylene or ethine? That had a triple bond, didn't it? A carbon-carbon triple bond. So, as I just mentioned, the first bond has to be the sigma. So, I have two more bonds between those two carbon atoms of the alkyne. Those other two bonds must be pi's. So we need to talk about this pi bond for a minute, because that's going to be an important part of our discussions as we go further. So let's come down here a little bit, raise this up slightly, and let's talk about this pi bond. So here's the sigma bond between the two carbon-carbon atoms. The pi bond is this bond that is not between the atoms, but is above and below. I know it looks like there's two bonds here. You see these two blue things? That is not two pi bonds. That is a single pi bond. A single pi bond has two overlapping areas. So you remember our hashes and wedges. So here's a carbon atom and here's a carbon atom. You can kind of think of this as being tilted. So this hydrogen and this hydrogen are going away from you, behind your computer screen right now. And this hydrogen and this hydrogen are coming at you. And this bond is in the plane of the piece of computer paper there. So this is a right angles to this plane. This pi bond is at right angles to this plane. So this molecule, ethylene, is flat and it's trigonal planar. Remember, valence shell electron pair repulsion. We have one bond, and now it doesn't matter if it's one bond, two bonds, or three bonds. We consider this whole thing as being one repelling unit. And then we have this third repelling unit. 1, 2, and then all of this 3. So this is flat trigonal planar. See this angle right here? This is 120 degrees. Let me get my pencil here for a second. If I can find it. Here we go. So, do you see this angle right here? That's 120 degrees. That angle is 120 degrees. This angle, carbon-carbon H angle, is 120 degrees. Because that is the angle that when you have three repelling things, that is the angle. And remember, repelling things are more than just single bonds. They can be double and triples. So here's one repeller. Here's a second repeller. And this whole thing is the third repelling unit. So there's the carbon atom that has 3 things that want to get away from each other as far as they possibly can. And that angle then is a trigonal plane. So alkenes are trigonal planar. Okay, they're flat. Now we have to talk about some other things related to alkenes, and we're going to continue. So, let me get back here. So the other thing to note about pi bonds is they are electron rich. They have a lot of negative character to them. And therefore, later on, we're going to see that the pi bond attacks positive stuff. Remember, in chemistry, opposite charges attract. They are an interacting pair. So we have this electron-rich pi bond that can go out and attack positive things. We're going to see this when we talk about the synthesis of ethylene in a different way from alcohols. All right, so let us now talk about another aspect of alkenes. Here I have a different starting material. Here I have a different hydrocarbon. We have 1, 2, 3, 4 carbons. So this is isobutane, or in the IUPAC nomenclature, 2-methyl propane. Now notice what I've done here. I have labeled these carbons with this, it looks like a little symbol that says 1 degree, 1 degree, 1 degree. And then this carbon, what looks like 3 degrees. This has absolutely nothing to do with temperature. This is a designation of the carbons and how many hydrogens that are attached to them. A primary, that's what this 1 degree is. This means primary, has 3 hydrogens attached to the carbon. Primary carbons have 3 hydrogens attached to the carbon. Tertiary, the 3 degree one, is called tertiary. Here's a carbon atom that holds only 1 hydrogen. 3 carbons, 1, 2, 3 carbons. That's tertiary. How about you do this one for me? If a primary holds 3 hydrogens, a tertiary holds 1 hydrogen, how many hydrogens would be on a secondary carbon? Pause. I should have a Kahoot. I wish I would have done a Kahoot here. This would be a nice Kahoot question. But I'll go ahead and tell you the answer. A secondary carbon, 2 degrees, holds 2 hydrogens. Primaries hold 3, secondaries hold 2, tertiaries hold 3. What if you had a carbon atom that had no hydrogens? That would be called a quaternary carbon, 4 degrees. All right, so that just is a designator for the carbon atoms. So if you had a carbon atom then that had this tertiary hydrogen and you subjected it to those free radical reaction, okay, here's bromine and light, just like we did before with ethyl bromide. Look at what happened. The molecule that you derived put the bromine on the tertiary carbon. Wow, statistics doesn't bode well for that, does it? Look at how many hydrogens are on primaries. 3, 6, 9. There are 9 primary hydrogens and only 1 tertiary hydrogen. So statistically speaking, you would have said that 9-to-1, the bromine should not be on this middle carbon. It should be on one of these outer carbons. But look, 99% of the product is this molecule. So that tells us something about the nature of hydrogens when they are on primary, secondary, or tertiary. Tertiary carbons are far, this greater than. Tertiary carbons are much more reactive than primary carbons in terms of their reactivity to free radical halogenation. Now, what do you think secondary carbons would be? Secondary carbon hydrogens would fall right in between, right? They'd be in the middle. How about quaternary carbons? Okay, that's a trick question, right? Quaternary carbons don't have any hydrogens on that atom. Sorry, I don't mean to trick you, but that was a kind of a trick question. So we only have hydrogens on primaries, secondaries, and tertiaries. All right. Now, let's go ahead and take our product that we just generated from this free radical halogenation. Here it is. And now all I'm going to do is heat it up to do an elimination. Now notice what happened here. This bond between the carbon and the bromine broke to form this new carbo. This is called a carbocation, a cation. Sometimes it's called carbonium ion. Now notice, let's go back. We did not get that in this reaction. When we took the base and pulled this hydrogen off, there was no carbocation that formed. Yet, let's go over here. When we have the bromine on a tertiary carbon, we get the cation. So there's something about these stabilities of cations that I have to mention right now. So a tertiary carbocation is very stable compared to one that would have been back here on a primary, right? This over here is a primary. So that's not something that forms very easily. So this is an intermediate. Notice what happened here. No base was involved here. The base is not involved in the creation of this intermediate. So there's only one molecule that's involved in the generation of our transition state molecule, our intermediate. That's what this 1 comes from. Elimination unimolecular. One thing to get to here. This is the slow step, the rate determining step. Now, once we get this, then a base, in this case, we can just use the bromide that we lost as our base. The base then comes in, hits the hydrogen, and forms the alkene, okay? So there is a difference. These substrates are very particular in their reactivity. So depending upon whether you're primary, secondary, or tertiary alkyl halide, go ahead and put that in. Primary, secondary, or tertiary alkyl halide sends you down either E2 path or E1 path. All right, very complicated. Now we're starting to get into some heavy chemistry. Will I ever ask you to draw this mechanism? Absolutely not. Will I ever ask you to name any of these things? I will not. Will I ever ask you what is a primary carbon? I will. Will I ask you about a tertiary carbon? I will. Will I ask you about the different reactivities of primary, secondary, or tertiary? I will. That's the stuff I need to know. That will be on that Moodle page, what do I need to know section. I will tell you that. So if you didn't get it right now, don't worry about it. It'll be in the Moodle page. All right. So elimination reactions can go either E1 or E2 to generate these alkenes. Oh. Now, before I leave this, I had mentioned that these pi bonds are very electron rich. They attack things. So later on, so here, let me go ahead, emphasize this. Electron rich pi bond. Negative attacks positive, always. Negative things attack the positive things. So later on, when we get to reactivity of alkenes, we're going to look at how that pi bond attacks positive things. All right. So alkenes then vitally important in a lot of different, as both a starting material for other things, as well as a precursor to important consumer products like polymers. Polymers not today, polymers next class. So be prepared for that, especially you material science people. All right. Now, I promised to tell you about another way to make alkenes, not from alkyl halides, but from alcohols. This reaction is known as a dehydration. You know, to hydrate means to add water, right? So if you go to the gym and you go for, you do your workout and you get thirsty, you need to hydrate, right? So what do you do when you want to hydrate? You go to the water fountain or you get your water bottle and you drink a lot of water to put water inside your body. That's a hydration reaction. But a dehydration reaction is when water comes out of the molecule. Just like when you were exercising, you were sweating. And so water, that perspiration was coming out of your body. You were exhaling. You were breathing really hard on your run. So you got rid of a lot of water. Okay, that's called a dehydration. So here is a reaction in which we're going to take an alcohol. Here's ethyl alcohol. We learned about alcohols in a previous lecture. Alcohols are ROH. All alcohols are ROH. ROH. In this particular case, the R is the ethyl, CH3CH2 group. It could have been, now you can't do this with methanol because we don't have enough carbons, but we could have done this same reaction with pentanol, with cyclohexanol. What's cyclohexanol? So these reactions can also take place when the alcohol is part of a hydrocarbon in a ring. Cyclohexanol. Okay. But again, you don't have to name anything. You don't have to draw any structures. You just have to know that this reaction is kind of universal. So I can dehydrate this just as easily as I can dehydrate ethyl alcohol. Now, what do I need to dehydrate this? Well, first off, I need an acid as a catalyst. In this particular case, I'm using sulfuric acid, and notice I have highlighted concentrated sulfuric acid. Why concentrated sulfuric acid? Why can't I use hydrochloric acid or hydrobromic acid or perchloric acid? Well, those other acids contain a lot of water, but concentrated sulfuric acid contains very, very little water. And notice, water is the product of this reaction, right? You can remember back in Chem 101, in general chemistry, there was a principle called Le Chatelier's principle. So in principle, this reaction can go back the other way. So a dehydration is basically a hydration in the opposite direction. So how do I maximize the black arrow and minimize this red arrow? I want to make alkene. This is my desire. I got to make sure I get rid of this water. So I'm going to take the alcohol. I'm going to use very, very dry acid so there's no water around. And then I'm also going to heat this up to remove the water. I'm going to distill off the water. All right. So basically, the acid just basically turns this group here, this OH group, into a good leaving group. This is a good leaving group. This is a bad leaving group. OH minus, bad leaving group. Let me get a different color here. Let's get green. All right, I made it blue. That's fine. Bad leaving group. Let's look at this. Good leaving group. Now, why is that such a good leaving group? Because in generating the leaving group, I generate a neutral small particle. If you to generate this, you generate OH minus, which is an ionic molecule. So that's what makes this a bad leaving group. OH minus bad, H2O good. So here again, it's a beta elimination, just like before, beta. Here's the alpha carbon, alpha because it holds the leaving group. Now it's not a halogen, it's an OH, it's the water particle. The water comes in, pulls off the adjacent beta hydrogen, and forms our pi bond, our electron-rich pi bond. The sigma bond hasn't gone anywhere. It's still there. All right. So that's an alcohol dehydration to generate the same ethylene. So I've got two different ways to make alkenes. I can dehydrohalogenate. That's what alkyl halides did. I can dehydrohalogenate an alkyl halide and make an alkene. Or I can dehydrate an alcohol to make alkenes. Two ways to get to the same material. So a very, very powerful process. Let us continue. A lot to do today. All right. I want to do a dehydrohalogenation on 2-bromobutane. Don't worry about the name. Basically, this is the 1 carbon, 2 carbons, 3 carbons, 4 carbons. So this is the number 2 carbon, so I call this 2-bromobutane. I'm going to do the same thing. I'm going to do a dehydrohalogenation reaction. Again, do you remember before? This carbon out here is primary. So this CH3 is on a primary. This CH3 out here is also primary. This bond right here, these two carbons are secondary. Okay, so it is these hydrogens that are most susceptible to dehydrohalogenation. So if I take my base, I am going to remove, oh, I don't want that color. Let me get rid of that. Let's go to black base. It's going to remove one of those hydrogens. Now, here's a big thing to remember. Will I ask you this? I certainly absolutely will. See this carbon-carbon-bromine, carbon-carbon bond in this 2-bromobutane? There's free rotation. This can spin like a propeller on an airplane. It can spin around. So there's free rotation about carbon-carbon single bonds. Now, once we remove that, we make a carbon-carbon double bond. But notice in a carbon-carbon double bond, there is no free rotation. I cannot spin around a carbon-carbon double bond. It's as though I've locked this in. I've locked it in place. So I've frozen this methyl group here and this methyl group. Think of this like a road. And on the road, there's one side of the road and the other side of the road. So here is so if this is Hillsborough Street and DH Hill is over here, then the OIT, the computer center, is over here. So this is a highway that you can't flip around. Now, but I could have easily, since this spins around freely, I could have easily have rotated this methyl group down here. And then if my base comes in this direction, I can create the cis isomer. See how I have a methyl group, double bond, methyl group. Now these two methyl groups are on the same side of the street. We call this cis. When the two groups are on opposite sides of the double bond, we call that trans. So this is yet another kind of isomerism. We call this a stereoisomer, but not in the sense of stereoisomers that we learned before. These are geometric isomers. Stereoisomers, configurational isomers, constitutional isomers, and now we have geometric isomers, cis and trans. Now, the other thing about this is there's another cis or trans that we haven't talked about yet, and that comes from hydrocarbons. So I'm going to pause here for a second. Before I start talking about the chemistry of vision, I want to talk about this cis and trans double bond. There's another cis and trans when there's no double bonds. And how I'm going to do that is I'm going to bring up our textbook here for a second. So I'll stop our share. And then I'm going to bring up our textbook and let you take a look at a particular chapter in one of our textbooks. So I'll share again. And let me bring up, let's see, where is it? Not there. Bring up so many different windows open here. Let me pause that for a second. Let me find our textbook reel. I might have closed it inadvertently. I think I may have. Let me go ahead and bring up our textbook again. Thought I kept it open. Oh, I did. Here it is. Okay. All right. So now I found it. Now I just got to share that with you. So let me share my screen. Come back to our homepage here for a second. All right. So now I have a page open in our textbook. This is the General Organic and Biological textbook. So if you go to the Moodle page, this is the first textbook of the 3 books that I have listed for you. So here I have butene, and here I have butene. Look at this. CH3, C double bond, CH, CH3. Butene, butene. Well, if I have 2 different butenes, I got to call them different things. Cis-butene, trans-2-butene, 2 meaning the second carbon, 1, 2, 3. Because obviously we could have a 1-butene too, right? If I had the double bond between the first carbon and the second carbon, that would be called 1-butene. But because this is starting off on the second carbon, it's known as 2-butene. Now, these molecules, they may look identical. Everything's attached in the same way. It's just structurally, geometrically, they are different. Cis-butene and trans-butene have different boiling points. They have different melting points. They have the same exact chemical formula, but physical properties of these 2 molecules is very different. Okay, so here's cis-butene, methyl, C double bond. So I'm coming down the street. I stay on the sidewalk and I stay on the same side of the street. Trans-butene. Here I am on this side of the street. I walk along the road and then I go on the opposite side of the road. So here's trans-butene. Cis and trans 2-butene. Okay. Now, there is another way to get cis and trans if you don't have a double bond. Let's go back to our hydrocarbons and let's talk about things that are in a ring. So you see these carbon-carbon single bonds? If you were to draw a model or build a model where you had a cyclic structure, there would be no free rotation about these double bonds. They're locked in position. So notice when you have a ringed hydrocarbon, basically you have 2 faces, the top face and the bottom face. And if the 2 methyl groups here are on the same face, we call that cis cyclopropane, dimethyl cyclopropane. If the 1 carbon CH3 and the other carbon CH3 are on opposite sides of the ring. So just think of holding your hand up, and you have the back of your hand and the palm of your hand. If both are on the same side of your hand, both are on the back side of your hand, that's known as cis. If you hold a finger up and 1 finger down, if you put your pinky up, and that's pointing towards the back of your hand, and then put your thumb down towards the palm of your hand, that is known as trans cyclopropane, 1,2-dimethyl cyclopropane. So you see, cis and trans can apply to 2 different issues in organic chemistry. One that is on ringed compounds, and the other one has to do with carbon-carbon double bonds. So if you wish to, you could get on your page here and they give you some examples for you to try. Which compounds can exist as cis and trans geometric isomers? And then maybe you want to draw these out on a piece of scratch paper. So again, this I told you in your schedule which chapters in the books that you could read. So obviously this is a cis and this one's a trans. So they just did this one for you here. See number 1 here? They worked the solution out for you here in the first one. Okay. So again, this is a nice way for you to build your skills your problem-solving skills. Obviously, doing homeworks is one way, and I'll probably give you a couple of these for homework questions. And this is another way to build your confidence. A lot of people say, I'm just not confident. I need more problems. I want to try more problems. Well, go to your textbook under those readings I gave you and try a few of these. Now, don't go right here immediately. Don't look at the solution before you actually give this a try. Give it a try, then come down. Did I do it right? And then you could see, oh yeah, I did this correctly or I didn't do it correctly. Okay. So it's another way to get more practice. And there's some concept problems here as well. So you can try those. But again, so where do you find this? This is that first book. Look way up here. This is page 637 of that particular general organic and biological chemistry textbook, or again, chapter 13, as I mentioned in the schedule. All right, so let me get out of our textbook. I think you probably have a good idea about cis and trans as it applies to two different issues, as it applies to double bonds and as it applies to cyclic systems. There is no such thing as cis and trans in triple bonds because those molecules are linear. And so there's no such thing as a triple bond that is cis and trans. All right, I'm going to stop that share for a minute and come back to our lecture. So I want to get back to our, I'll share my screen again and bring up my notepad because now I wanted to talk about vision. Everything we do this semester is there's going to be the underlying chemistry, and then there's going to be the application to the real world. Look at everything we've done. Everything we've done is here's some fundamental chemistry issue, and here's how it applies to your real life. That's what this class is about. Chemistry in your life, which I will talk about in a moment when it gets to your project. We're gonna end today with a brief overview of the project. Again, the project is not due to the end of the semester, so don't freak out. It's still got a long ways to go, and we will flush out the details about the project as time goes on. So share my screen with you again and get my notepad up here. And make this big so I can see it. Okay, so here's trans, here's cis. Notice what I've done here in green. I've taken this pi bond and I've isomerized it. Isomerization means to convert one into the other. This is locked. Trans is locked. Cis is locked. Yet, by shining light of a particular frequency on this pi bond, not the sigma, on the pi bond, I can convert the trans into the cis into the trans. So I can do this isomerization reaction. And this basic mechanism of going from cis to trans is the whole reason, unless you are blind, and I apologize immediately to anyone who might be blind. I think we have one severely visually impaired student in the class. So you are hearing me through words, not through photons. But for those people who don't have any visual impairment, you are seeing me through this reaction. Cis goes to trans, trans goes to cis. This is basically the chemistry of vision. Let me go. All right. I know this is a very complicated molecule. Don't worry about it. I will never ask you this. I will ask you the name of it. It's called retinal. Retinal. Copy that down. Retinal. Let me get my pencil out here. I'll choose red. Retinal. Cisretinal and transretinal. I'm sorry, my T got chopped off there. That should say right there, that's a T. It's not ansretinal, it's transretinal. And it has to do with a particular bond that's in your eye right now. This is what we call a chromophore. Chromophore, that's a fancy way to say a molecule that absorbs light. There's a good definition for you. Will I ever ask you about what is a chromophore? Oh, you betcha. An organic molecule doesn't have to be organic, but in our case, since we're taking organic chemistry, a molecule that absorbs light is called a chromophore. In this case, we want to absorb visible light because that's what our eyes see. Our eyes see visible light. Is that the only kind of light? No, there's lots of light. Light is just one tiny, tiny little fraction of the electromagnetic spectrum. We just had the James Webb Telescope. Billions of dollars we spent to send this telescope to outer space to view not visible light. What is the light that the James Webb Telescope is looking for? Infrared light. The light from hugely, vastly distant galaxies. Basically looking back in time is what the James Webb Telescope will allow us to do. It's not up and running just yet, but it's in place. It will be up and running soon. I think they said by March, they'll start getting the first images. So if you thought the Hubble Space Telescope was impressive, just wait till you see what the Webb Telescope has to offer. All right, so what does it make this molecule such a good visible light absorber? Well, it has to do with conjugation. What is this word conjugated? Well, this is a pattern of double bonds and single bonds in a molecule and alternating double and single bonds. So here we have a single bond, a double bond, 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 a single bond, and a double bond to this oxygen. So you see this extended network of sp2 of carbon atoms that are all in the plane. These are all planar. They all have p orbitals. Remember, that's what makes this pi bond. A p orbital here, a p orbital here, p orbital here, p orbital here, p orbital here, a p orbital here, over and over and over again. This extended network of overlapping p orbitals that allows for the absorption of light. The more conjugated you are, the further towards the red and infrared. The less conjugated this chromophore is, the more you go towards the blue. So a molecule like ethene, that we started out with today in class, it absorbs light at about 190 nanometers. Very, very short. That's ultraviolet light. Whereas this molecule absorbs light around 450 nanometers, the visible end of the spectrum. So how is this working? How is my eye perceiving a photon of light hitting my eyeball? Well, it's going to take this bond right here, this one right here, and it's going to convert it from cis to trans. See how this cis one looks like it's bent? Looks like a horseshoe, doesn't it? The absorption of light causes it to go much more linear. Well, this dye, retinal is a dye, you can think of it as a dye, absorbs light, does this conversion, and on this dye is attached a protein called opsin. So the combination of retinal and opsin is rhodopsin. And so the brain interprets this conformational change in the protein, this opsin protein, as I have just absorbed a photon of light. Here's the photon of light. Bambo, hits the cis, goes to the trans. Well, how does that work? Remember, I told you, there is no free rotation about this double bond. But here's how it works. The cis absorbs the light, then it creates a di radical. An electron here and an electron here. Now notice what happened. these two electrons of the pi, one electron went to this carbon, one electron went to this carbon. There they are. Now I've got a carbon-carbon single bond. Carbon-carbon single bonds can rotate. They can flip around. So this can spin around and convert to the trans isomer. Then later on, a series of enzymatic reactions takes it back to cis. Cis to trans, trans to cis. This is basically the chemistry of vision. So conjugation in order to get the wavelength of light we need, the visible end, and then the isomerization to make it into that particular isomer. All right. All right, so that is it for this particular lecture. I've only left about 15 minutes left. So what I want to do now is just briefly describe, oh, sorry, did I have a question? I'll leave some time right after this to do a question. Sound like a puppy. Okay, so. %20 of your grade is going to come from a project. So this project will be a particular analysis of how chemistry, organic chemistry, impacts your particular field. Now, that's very broadly stated, isn't it? How does organic chemistry impact your field? So let's say you are just for an example, i.e., let's say I am a nutrition major. This is going to be different for everybody. Maybe you are turf grass, maybe you are ag life science, maybe you are environmental science, maybe you are textile major. Whatever your major is, I guarantee you organic chemistry has impacted your field in some very meaningful way. And this is what I want your project to be. I want you to choose a particular, it could be a lot of things. It could be one molecule. Perhaps it's a single molecule. How has this molecule impacted the field broadly of nutrition? So let's say in nutrition, I want to analyze glucose. Don't worry about the structure of glucose yet. Glucose is a sugar, a simple sugar of 6 carbons, very important in our bodily functions. It's what is powering your brain right now. A lot of glucose is metabolized in the brain, and glucose is also metabolized a lot in your muscles. That's what gives you the energy for you to move around and to exist. So maybe you want to do a project on glucose if you're a nutrition major. What aspects of glucose? Well, first off, you have to generate why. Why is it important? The history. Who discovered glucose? The synthesis or biosynthesis. Obviously, most of you have had biology, so I don't have to tell you about photosynthesis. But how is glucose made and where is it located? Most of the glucose we get comes from plants, right? Sugarcane or starches. So potatoes are basically a polymer of glucose. So that's a biosynthetic reaction. So obviously, how do I make sugars? I take CO2, I take water, I take light from the sun, have a plant, I make glucose. That's photosynthesis, right? We're gonna have a lot to say about that later when we get to sugars. And the plant might do other things with it. The plant may polymerize it and make amylose, starch. Okay. And starch comes from potatoes or other sources of grains. You get starch, and then that obviously then we can us humans We can take that starch, break it apart to glucose, and then convert that glucose back to CO2. There's the chemistry of life, right? So that's just one example of a project that somebody might do if I was a nutrition major. Then, in addition, what are the aspects of in my field of glucose and things that could happen awry? So you might want to talk about diabetes or insulin. You might want to talk about how glucose or polymers of glucose can be made into other products. So you catch my drift, and I'll have more and more to say about this as well. But what I would like you to start to do is I would like you to start thinking about whether it be a molecule or a class of molecules in your field that you might want to learn more about. If I'm a ag major, agronomy or whatever it might be, maybe I want to study something about pesticides and the history of pesticides, pesticide resistance. Why do pesticides work? And then why don't they work eventually? How are we overcoming pesticide resistance? What new methods can we design and develop that could cause that, where we could kill the insects, not hurt the plant, but then not cause resistance? And especially, of course, when it comes to pesticides, how do we find pesticides that won't hurt other animals? You know, Rachel Carson, you remember Silent Spring, that famous book from years ago, where certain pesticides were used to kill malaria, these insects. And then, okay, so malaria went away, but then all of a sudden birds started dying, and it created a host of other issues. And then all of a sudden, all these sprays that we used on the malaria didn't work anymore. The insects got resistant to it. All right, so that was kind of a long discussion about your project. But for now, all I want you to do is start to think about one molecule or a class of molecules in your particular field, and how did organic chemistry, this has to be something organic, by the way, which probably is not a big stretch. How did these organic molecule or molecules either impact your field in a positive way or a negative way? And then obviously we'll talk about a lot of the things about how you are going to show your molecule or molecules using your ChemSketch program, how to draw them. And again, if you get stuck with drawing more complicated molecules, I can help you with the drawing of these things, but you'll incorporate those structures into your paper. All right, so let me stop that share real quick. And finally, in the last 5 minutes, I will open it up to any kind of questions you might have. So you can go ahead and unmute yourself and let me know what you're thinking about or what kind of problems you have.
Dr. Brown,
Yeah.
can you post like a rubric or like a paper explaining like the whole project and like what to do and everything?
Absolutely. There'll be definitely a rubric which will include what parts of the project are worth how much. So like your intro paragraph, your definition of problem, your structure, your conclusions, all of those will be worth a certain amount of points.
And
Yep.
when is this project due?
Not till the end of the semester.
Okay.
Yeah, the very end of the semester. Correct.
Hi, Professor Brown.
Yeah.
I was just wondering, do you know when our next homework is going to be?
It's up right now, or it will be up in 15 minutes.
Okay, thank you.
It will be due on Friday night, 10 p.m. So homework 3 comes up at 1:15 and is due Friday night at 10 p.m. Anybody else? Oh, where can I find the content of today in the lecture? Oh, okay. Where do I find that? So let me open up Moodle real quick. There is no schedule about homeworks and when they're due. Homeworks come up randomly throughout the semester based upon when things will happen. So depending upon what I cover, that will dictate the next homework. So there's no schedule about homeworks. Are they always due on Friday? They always do on, they come up randomly throughout the semester based upon the content. But let me show you here real quick. So alkenes, where can I find the reading about alkenes in our textbook? You see right here where it says, let me get to the top, chapter readings, general organic and biological chemistry, chapter 13:1. So that is the what I showed you today. I brought up that particular section in the book. So if you want to know where those readings are, just keep following these readings here. Sometimes they're over here, by the way. If I run out of space over here, I'll put it over here. And then these can actually go for multiple different lectures. So this up here actually goes for here too. So if you read this, you're all prepared here because these fuels were also part of that discussion here too. And then this will be populated as we go through the semester. So I haven't populated these yet. So the alkene polymers, notice there's no reading on the alkene polymers yet. I haven't discussed alkene polymers. That's for Thursday's lecture. So you'll see that on Thursday. Oh, you can't even see that, can you? I didn't share my screen with you. Hold on a second. Let me go back. Zoom meeting, share screen. Here we go. Okay, now you can see it. So you see here, so today I was talking about alkenes and carbons, E1, E2 reactions. You see here GOB 13.1, chapter 13, starting at the first part of chapter 13. So here's where you will find a discussion of alkenes. So that person who wanted to know, where is that discussion? Okay, let me stop that share. Okay. Any other questions? You good? Okay, like I said, yeah.
Dr. Brown, I have a question.
Sure.
Well, I know that on the syllabus it says that there will be no makeup exams given. So obviously, like if
Right,
an
no
individual
makeup exams.
person-
So
yeah.
if you miss one, your final exam replaces that score.
Yeah, I was just wondering, like, if there are any policies in place, like if a large number of people in the class were to contract COVID, or like if the university COVID cases go like
Yeah,
up a
obviously
lot.
we have to be fluid. So let's say, God forbid, let's hope this doesn't happen. The numbers all look great. The numbers are looking really good. And I'm knocking on wood right now, because obviously that could change if a new variant comes up. So let's say a new variant, the Omega variant comes up, and this variant is so virulent that anybody that comes within 20 feet of a COVID patient will immediately contract COVID and then have to go to the intensive care ward and get on, be intubated. Now, obviously, I don't predict that to happen, but if it did, we would certainly have to change our policy. So at that point, we probably have to go to something like, if a large number of people were in the hospital, we'd have to give everybody incompletes, and they'd have to come take it another semester. That's just, we don't predict that. So let's say that doesn't happen. So if the university comes and says, okay, it's not safe, we've got this new variant, so in 2 weeks' time, all of a sudden the numbers all of a sudden went way up. We'd have to change our policies based upon information given. We always use the information that we have to make good decisions, scientific decisions. Scientifically, right now, the likelihood of anybody getting sick from COVID is getting very, very remote, especially if you have been vaccinated. I, by law, cannot ask anybody their vaccination status. I don't know who has been vaccinated and who has not been vaccinated. I don't think, I'll have to check this, but I don't think public universities can demand people even wear masks. I might be wrong about that. I'll check that. But, you know, can I say to somebody, if they come into the test without a mask, you know, put your mask on or you cannot take the test? I don't think I can even do that. So there are some risks involved. And for anybody that's really nervous, I have a plan for you. I have a way to separate you by at least 20 feet from the nearest person during the test. So I can put you way down in front towards the corridor. And so you won't have to get anywhere near anybody if you just are really nervous about catching the COVID from somebody. So right now, I plan on having class next week in class. And then the following week after that, I plan on having the review session in class. I plan on having the test in class. And hopefully everything will go fine. But certainly if the university comes back and the university says, oops, we made a mistake, COVID numbers are skyrocketing, obviously we'll have to make a change. Any other questions? All right then, well, I wish you all a good Tuesday. Remember, there's a homework number 3, that is coming up live for you this afternoon at 1:15 p.m. It will be due Friday at 10 p.m. Okay? Hasta luego.
Hey, Dr. Brown, real quick.
Sure, go ahead.
I don't want to ask it on here because everybody's on here, but is it okay if I shoot you an email? I had a question about the whole class and stuff like that.
Anybody can always send me emails anytime. So you got a question, just
Yeah,
email me your question and I'll get to it as soon as I can. Now, it may be a few hours or maybe even the following day, but yeah, you got a question, always open to emails. So anytime you got something, just email me your question. And the nice thing about that is then I can put a molecule in the response too.
Okay. I'm definitely going to do that because it's more of a personal question, but thank you.
Okay, you're welcome. All right. Bye, everybody.